we have two ways that we're able to move charge, positive or negative, through through our block of silicon. Okay, and so one is that we apply a voltage. Honestly, we have a block of silicon. We hook up a battery, and we see electrons will go this way, and holes will try to go this way through our electron. But we're basically applying an electric field to push them through is really what's going on. We call this drift velocity or drift mobility, drift current. Okay, and so drift velocity, and so I'm going to draw it's not a v, it's a velocity. Well, it is a v, but P drift is due to the holes, and that's equal to something called mu p times the electric field. So we're applying an electric field this way. Okay. We also have the n drift. I think that's a nu is what that is equal to mu n, and we'll have to define the mu n and mu p here in a second. And this has a negative value on it times the electric field. And this is because we have to set it to be in opposition to the electric field. It's going the opposite direction. Mu p is the whole mobility, okay? And this is equal to 480 for silicon. This doesn't change much for silicon. 480 centimeters squared per volt second. Okay? We also have the mobility for electrons is different. It's much bigger. It's easier to move an electron than a hole. So 1350 centimeters squared per volt second. And so that gives us those values for those two things. Now I wish I could keep my entire screen in focus at once. I might have to adjust that. But mu n, mu p are going to be some values. So hold on to these two values. Know that these two exist. And then we have a total, okay, that's going to be basically the aggregate of these two. But first we're going to break it into, we'll just use the whole board here, is what we call IP. This is the actual current, is equal to the cross-sectional area of whatever we've got, charge of an electron, number of holes that are in per centimeter cubed, and then times Vp drift. Okay? In is going to be the exact same thing. Okay? Except there's a minus sign. Minus sign in opposition to this minus sign. It's in opposition to that minus sign, so that both of these add up to be positive. Okay? And just so that we're completely confused about this, let's start over here top left. We're going to start over here top left, and we're going to call the current density, which is denoted with the JP, is equal to IP over A. That's it. Okay, it's just saying it's dividing it by the cross-sectional area. This is really easy. Q times P mu P times the electric field that's being applied. Okay, and we can do the same thing for Jn. This is the current density over A is equal to Q minus Q. I take it back. So we're just going to say Q, right? Because IN was negative, and so this one's also going to be positive. Q n mu n times E. And then combining both of those together, we know that the charge density, or the current density, the total current density, is equal to Jn plus J sub P. That's the entire thing put together, and we can even break these out, and we can pull out the Q, n times mu n plus p times mu p, all multiplied by that. And a lot of people call this J is equal to sigma E, where this is sigma is the conductance. And that's getting into some familiar territory for a lot of you, or hopefully for everyone. So sigma is equal to 1 over rho, and conductivity is, and rho is resistivity, but this is just equal to Q times N mu N plus P mu P. Sorry, that's not a subscript. Okay? What this means, resistivity and conductance is equivalent to resistivity and, this is not conductance, this is conductivity. Resistivity and conductivity is to resistance and conductance. Okay? And so all we have to do is figure out the other way. So that means rho, okay, is equal to 1 over this entire thing, Q mu N times N plus P times mu P. So this entire thing is kind of interesting as far as we're getting resistivity is in ohm centimeters, units of ohm centimeters. So all we have to do is take away how long it is. So let's review on resistivity. Resistance is equal to rho L over A. In other words, if I have a block of material, I'm going to try to draw it in 3 dimensions, has a cross section, has a length, and I try to measure the resistance from one side to the other. I can, if I know the resistivity, I multiply it by the length and divide by the cross-sectional area, then I get resistance. Okay? And so this makes a lot of sense. We take a conductor, we make it twice as long with the same cross-sectional area, and it gets twice as resistive. Okay? But the material itself has the same resistivity. In other words, copper always has the same resistivity. But when we change the physical size, it's going to change what the resistance is. Okay? And so that's kind of important because what we just found is the resistivity of silicon. And the reason why that's so darned important to us, and I think it's super important for us, is that when we get the resistivity from this, we know how this behaves like a conductor, like a resistor. And that's something that's very important. So let's go ahead and calculate this for an example. Okay? The first example that we have for this is that we're going to have a P, let me see, we want to calculate this for intrinsic. So P is equal to N, that's A. We want to calculate the resistivity. So A. B, N donor, P-type silicon, my bad. This is going to be P-type silicon, and A is equal to 10 to the 16th per centimeters cubed. We also want to calculate the resistivity for, let me see, the third one is, maybe that's it. Maybe it's only A and B. Okay, so we want to do this. They've given us a whole bunch of other information. We're going to go with the mu n is equal to 1350 value that we had before. Mu p is equal to the 480 value that we had before. They've given us ni as well. 1.5 times 10 to the 10th. And then we also have, let's see, per centimeter cubed. And let me see. They gave us different values for the doped silicon. So for the doped silicon, they said mu n was equal to 1110. And mu p was equal to 400. That's kind of surprising to me because that should be a constant. and they just want to know the resistivity. So we don't need to know the physical size, we just need to know what this is. And so if we go back to this, rho is equal to 1 over q, charge of an electron, mu n times n plus mu p times p. Okay, and so we have to calculate all this out. Now, for our first case, n is equal to p is equal to ni. Why? Because this is an intrinsic piece of silicon. There's just as many holes as there are electrons. And so this is going to be 1 over q. I'm going to leave that there. And all of these should be 1.5 times 10 to the 10th. And then we also have mu p and mu n, which are up there as well. So we're going to crank this into MATLAB. We're going to say, so I'm going to keep with what they have, ni is equal to 1.5 e to the 10th. Okay. 1.5 times 10 to the 10th. Okay. We also have mu n is equal to 1480. Mu p is equal to, 1350. Mu p is equal to 480. 1350. Okay. And then we also, let me see, q is equal to, and I should have this saved someplace, 1.6 times 10 to the negative 19. And we're going to start with, we're going to do just exactly what we have here, 1 over q times mu n times n I plus mu p times ni. And that gives us 2.72, so 228 kilo, let me see, the 228 kilo ohm centimeters, okay, 2.28 times 10 to the 5th ohm centimeters. That doesn't mean much to you, but that's a big value. That's not very resistive. Okay, it wouldn't work out very well if you try to make that into a resistor or a conductor. Resistor would work great, but this is not very good for as far as what you'd want to do. So a cubic block of a cube block of silicon is going to be 228 kilo ohms, which is big. The electrons don't move very easily in there. So we're going to do this next one, and I just want to point out, so we know what P is. P is approximately 10 to the 16th. But N, we're going to have to calculate, and this is going to be Ni over P for this one. Okay, so we'll calculate that. We'll put it through the same thing, but we have different values of mu N and mu P, which I still think is rather weird. Mu N, our new mu N is equal to 1110. Mu P is equal to 400 now. P sub P, I'm going to say, is equal to 10 to the 16th. By the way, common mistake on this is I could have said something like P is equal to 10 e to the 16th. That's a different number. That's actually 10 to the 17th. N sub P is equal to Ni to the 2nd divided by PP, which is 22,500. And when you come back to this equation that we have right here, when you come back to this equation and you say which one is going to win, mu p times p or mu n times n, p is so much bigger than n that this just goes away. I will calculate it both ways, and you can tell me which one you think is which one you'd rather calculate. So as I go through this and the little MATLAB window here, 1 divided by, and I'll just use this one they have here, mu sub n. So I'm just going to put np mu p times pp. Okay, so 1.5625 ohm. Okay, and I think I did something wrong. It's not matching up with what they've got here. But if I just simply left this part out, it's the same value. But there is something different than what they've got here in their equation. Nope, we did it right. So 1.56 ohm centimeters is what we get for an answer for this one. So you can see that's how many orders of magnitude difference is this? At least, you know, 2 times 10 to the fifth orders of magnitude different, just by adding a really small amount of dopant, if you want to think about it that way. So what that is one way. So going back to this is one way that we can move current through there, is by applying an electric field, or by unevenly distributing the hole's electrons. But okay, so this is called drift current. Okay. There's also the one that's coming up is diffusion current. Slightly, way different, but that one's probably the more important one that we'll get to in the next lecture.